everyone, and welcome to today's edition of our Distinguished Lecture Series with Shanhui Fan. So, as you all know, the Distinguished Lecture Series is our main event at the Max Planck Institute for the Science of Light to invite the international thought leaders in the science of light, and also hello to people who may be joining us online. So I want to say a few words about our today's speaker. He's the Joseph and Honmai Goodman Professor of the School of Engineering at Stanford University, with appointments also in applied physics and the Precourt Institute. So Shanhui came from China originally, where he did his undergraduate education, and then went to MIT, where he finished his PhD in 1997. After staying on in MIT or the area for a little while, he then was appointed assistant professor at Stanford University in 2001, rose through the ranks, also becoming head of Goodman Laboratory, and today has the titles that I recounted in the beginning. So he's very well known for his pioneering work in nanophotonics in general, involving, for example, pioneering works in photonic crystals, plasmonics, and metamaterials, with applications nowadays in the areas of topological photonics, non-Hermitian physics, and optical neural networks, which of course overlap very well with many of the things that we are doing here at the Institute. In addition, he has done research of a much more applied bent recently, for example, looking into solar cells or especially passive radiative cooling, where he has also co-founded a company, SkyCool Systems, one of the two companies he co-founded. He has won numerous awards. Just last year, he won the Wood Prize of the Optica in 2022, the Simons Investigatorship in Physics 21, various other fellowships, for example, APS and OSA, or the Adolf Loom Medal of OSA in 2007. And despite being primarily a theoretician, he also does experiments, and much of what he does is very applied, which you can read off from the fact that he holds about 70 patents. So with that, I want to stop the introduction so we can go on to the talk. We are very much looking forward to the exciting physics that you will bring us, Shanhui. Please.
Well, thank you, Florian, for the very kind introduction. And I'm also like to thank Vahi and the Institute for hosting me here for a month. So I'm actually staying here for the month of July. I have already talked to a number of you, and I certainly look forward to further discussions. So today I'd like to talk about some of the work that we've been pursuing in the past 6 or 7 years in a concept we call synthetic dimension. So as a background, as Florian mentioned, I have a background in photonic crystals and work on metamaterials. And in these things, the typical way you would do study is to try to come up with complicated two-dimensional or three-dimensional photonic structures. And in terms of physics, what you'll be thinking are the modes of these systems and how these modes couple to each other. On the other hand, if the essential physics is to think about the modes of the system and how they couple, there are in fact other systems that you can apply those physics as well. So in much of my talk, I'm going to talk about a completely different system, and that's just a ring resonator. And if you put a modulator in there, you'll be able to couple the modes inside the ring together. And in this case, the coupling is controlled entirely by the modulator. Now, as is typical in photonics, nothing is 100% new. So this idea that you should think about a modulated system in terms of coupling between different frequency modes, the system has a very long history. If you look at, for example, some of the pioneering work about mode locking of laser, at least one class of theoretical technique is built directly on this kind of idea. But what we do is to try to look at the same kind of thinking, but in a very different context of topological physics as well as optical computation. So with that, let me give you a bit of background. We got into this direction by thinking about topological physics. It is known, of course, that topological physics is very rich in high dimensions. So a few well-known examples are wild-point physics in 3 dimensions or 4-dimensional generalization of the quantum Hall effect. And these effects have no low-dimensional counterparts. So consequently, it would be good if you can come up with a nice experimental platform to allow you to explore these kind of physics experimentally. And that naturally leads you to the concept of synthetic dimension. The idea is actually a very straightforward one. Let's say, as an example, suppose you were tasked with trying to represent the 3-dimensional physics of an array of cylinders with varying heights. Then the natural thing that you would have done is to draw a 2-dimensional array of circles and then represent the height of these cylinders in different colors. In other words, what you have done is to take a 2-dimensional real space and add, you can call that a synthetic dimension, but essentially the color or the frequency to form a 3-dimensional space that you can play with. This idea has been around also in condensed matter physics, in atomic physics, and so on. But there really is a lot of potential of this idea in optical physics. So one of the main set of things that we'll be doing concerns the use of a ring resonator. It is well known that if you take a waveguide and wrap it around to form a ring, in the absence of a group velocity dispersion, the ring will support a set of resonances with equally spaced resonant frequencies. And the frequency spacing here is reciprocal to the round-trip time. Now, starting from this, you can put a modulator in there, and you can modulate the transmission function of the modulator in such a way so that the modulation frequency is equal to the mode spacing. When you do that, then you resonantly couple all the modes of the resonators together. So consequently, the dynamically modulated ring resonator system can be described by this one-dimensional tie binding model where the N here labels different frequency mode. So naturally, from a single resonator, which in a way you can think of as a 0-dimensional structure, you immediately get a 1-dimensional lattice physics. Moreover, the modulation phase here, let me press the send. Okay, yes. Yeah, still get used to this. So moreover, the modulation phase here, which is something that you can control on the microwave side, shows up as the hopping phase between different optical modes. And that's a directional dependent hopping phase, and therefore that's an effective magnetic gauge potential for photons. Starting from this, you can do a lot of topology. As a simple example, you can try to do 2-dimensional quantum Hall effect. One way to do that would be just to take a periodic 1-dimensional array of rings, and then within each of the rings, put a modulator in. In this case, you have 2 dimensions. This corresponds to a 2-dimensional lattice. One of them is the spatial dimension. So at every frequency, the photon can tunnel between the rings. And the other dimension is the frequency dimension, because now you have a modulator that allows you to couple between modes at different frequencies. Moreover, if you choose the phase of this modulator to be spatially varying, then you get a uniform magnetic field threading this 2-dimensional lattice. And that's the setup for creating a quantum Hall system. And a quantum Hall system has a one-way edge state. So if you truncate the system, you excite one of the lattice side on the edge, is going to go around only in a single direction around the edge of the structure. Here is the same drawing in terms of lattice. So you can also see this one-way edge state. But the interesting part of it is that part of the dynamics here is in frequency space. So, for example, if you excite this particular frequency in this resonator, first it's going to move up in frequency until it reaches the boundary, in which case it propagates in real space, reaching the other end, and then its frequency starts to go down. So in doing so, therefore, you gain the possibility of control the frequency of light in a topologically robust way. This, in fact, allows you to explore a large number of topological phenomena in synthetic space. Some of the things that we looked at are, for example, creating wild semi-metal, the physics of wild semi-metal, a three-dimensional topological insulator, or higher-order topological insulator, all built upon this platform. As just one example of a recent work, we have recently proposed to use this to study non-abelian gauge field in a synthetic lattice. In this case, it's very similar to what I have talked about the quantum Hall setup, except that we explore the fact that the fiber or the waveguide has both polarization. So therefore, each of these lattice sites, in fact, has a, you can call a spin label, but those are the polarization. And also, by separate those polarization out, and by modulate each polarization independently, one can create a non-abelian gauge potential and gauge field, and in doing so, study complex physics associated with these kind of setup. Now, this gives you perhaps a bit of theoretical background. Next, let me switch gear and talk about some of the experimental background. In topological physics, one of the very important things to actually measure is the band structure. And in this system, as I mentioned, you have a one-dimensional Hamiltonian that has a translational symmetry along the frequency axis. And therefore, the system also has periodicity along the frequency axis. And so you can also describe the system in terms of a band structure relating energy or frequency, in this case is the floor K frequency, to a wave vector. Now, the interesting part of the wave vector here is that you are talking about dynamics along the frequency axis. And therefore, the wave vector has to be conjugate to frequency. And the physical variable that's conjugate to frequency is time. As a result, to determine the band structure of the Hamiltonian of this system, you just need to do a time-dependent measurement. And so, more specifically, you can imagine that you have a laser shooting into this ring undergoing modulation. And because you have a modulator, and therefore the system is time-dependent, you should expect that the transmission will also vary as a function of time. And then you then collect the data of the transmission vary as a function of time, and you do that for different instant frequencies, and you collect them all together, you can form a diagram that looks like this. In this case, the peak, you're going to see peaks, and the peak will trace out the band structure of the system. So we build an experimental setup in order to play with this concept. In the setup, we have a fiber loop of a length of 13 meters, and that corresponds to a free spectral range of 15 megahertz. And in there, we put in a lithium niobate electro-optic modulator with modulation frequency up to 2 gigahertz, which is much larger than the free spectral range. As you will see, that's actually quite important to allow us to do what's called long-range coupling. And since this is a fiber setup, you can compensate away all the loss by semiconductor optical amplifier. So with this, then here is an experimental measurement of the band structure. So on the right, what I show here is the transmission as a function of time. As I vary, so each curve here corresponds to a particular frequency. As you can see, at certain frequencies, there are peaks. And moreover, as you change the laser frequency, the peaks moves. And now if you take all the data on the right and then collect them and generate a two-dimensional diagram that looks like this, then what you see here is an experimental measurement of a very nice looking cosine function, and that's the band structure of a tie binding band. Okay. So now I talk about using a single ring with a modulator to do one-dimensional physics. And in fact, with a single ring, you can do high-dimensional physics as well. So the idea is you, in addition to the term that has the modulation frequency equal to the free spectral range, you add one additional term where the modulation frequency is a large integer multiple of the free spectral range. In this case, if you look at it in a one-dimensional model, then what you have is a long-range coupling along the one dimension. But you can also take the same model and simply plot it differently. And so you can take this and, in fact, plot it in this way. In this case, the orange line is the omega r term, and the red line here is the high modulation frequency term. So in this case, you get a stripe with a twisted boundary condition, and the size of the stripe, the transverse size of the stripe, is controlled by this m parameter here. So consequently, you can generate a pretty sizable two-dimensional model or even more higher dimensional model in these systems. And again, you can measure the two-dimensional band structure in these systems. I mentioned this idea about measure the band structure by interpreting the time as a function, as a wave vector. And you can do the same thing, but the time here is just a one-dimensional variable. So if you do that directly, what you end up having is a sampling of the two-dimensional first Boolean zone, but only along a single line. So in order to sample the entire two-dimensional Boolean zone, as it turned out, what you can do is to play with the modulation phase on one of these harmonic. As you scan this modulation phase, you scan along different lines inside the first Boolean zone, and therefore, with this, you can scan out the entire two-dimensional Boolean zone. So here is an experimental result where we scan across the entire first Boolean zone of a two-dimensional lattice to allow us to reconstruct the two-dimensional band structure over the entire first Boolean zone. So this concludes the first part of my talk, where we talk about some of the theoretical and experimental background. Next, I'm going to show you a set of work, experimental work, where we use this platform to experimentally explore some of the important topological physics concepts. The first example I'm going to talk about is on Hermitian topology, where we get back to talk about the quantum Hall system.
Sorry, can I ask a previous section? So you're not really concerned about losses, right? And your losses are, what kind of loss do you have?
We actually have quite a bit of loss because we have couplers, and each of them has a few dB loss in there. But we put an amplifier in to compensate it back. So we're not doing quantum experiment. Yeah. So in fact, for these systems, it's not, at least in our setup, it's actually fairly straightforward to make a lace. So we actually have to be careful not to put too much amplification to make a laser out of it. Okay. So, but let me come back to the first experiment I'm going to show you on topology is this quantum Hall, getting back to the quantum Hall physics. So as I mentioned, if you have a stripe of a lattice and you apply a perpendicular magnetic field, then you create these chiral edge state, and you can plot out the band structure. You have a gap and one-way edge state that sit inside the gap, and outside the gap, you have the bulk bands that are extended inside the stripe. The quantum Hall system is actually quite a remarkable system in many ways. One of them is that, well, you can say, well, let me start with this system, but let me get rid of all the bulk. In other words, I only keep the two edges, but I get rid of all the bulk. When you do that, of course, you get rid of all the bulk state, but remarkably, the remaining state of this two-legged ladder system is still essentially have very, very similar characteristic of the edge state of a quantum Hall lattice. So you still see, for example, that the light that's concentrated on the left edge will propagate in one direction. The light that's concentrated on the right edge will propagate in the other direction. So the chiral behavior stays in this two-leg Hall ladder. So in other words, this two-leg Hall ladder, in fact, is perhaps the simplest system to really look at quantum Hall physics. And so we provide an experimental demonstration of the physics here. In the construction, again, we take a single fiber loop. Here, we form the leg of the ladder by considering both clockwise and counterclockwise mode. So the coupling along the leg is provided by the electro-optic modulator. The coupling between clockwise and counterclockwise mode forms the rung of the ladder. To do so, in a controllable fashion, we put in a figure 8 coupler inside the ring. In the figure 8 coupler, a clockwise mode will go through the blue arm of the coupler and come out as the counterclockwise mode. And the counterclockwise mode will couple through the purple arm and come out as the clockwise. Now, by choosing the length of these two arms to be different, we have a direction-dependent phase in these two coupling. And moreover, this direction-dependent phase is the wave vector times the length difference, and the wave vector scales linearly to frequency. So that gives you the linear chirp of the phase along the frequency axis. And you play the math a little bit, you will see that this is, in fact, a Hall ladder with a magnetic field threading a ladder system. And we can also have access to either the clockwise or the counterclockwise state. To have access to the clockwise state, for example, we send light from the left and measure the transmission. So that will predominantly excite and detect the clockwise rotating state. Similarly, sending light from the right and then detect transmission again would focus you on the counterclockwise state. So you can actually, if you call these things spin, you can actually provide a spin-resolved band structure measurement. So here are some of the experimental results. And this is, for example, an experimentally measured band structure focusing on the clockwise state. And you can see a distinct chiral behavior. For example, this particular band actually, which is a clockwise state, actually propagate predominantly only in one direction. So that gives you a sense of some of the topology that we can do in this system. In the next set of examples, I'm going to talk about some of the theory and experiments associated with non-Hermitian topology rather than Hermitian topology. So when you go back to band structure physics, in a Hermitian system, in the simplest one-dimensional one-band model, well, you have an E as a function of K, so you have exactly one curve. Now, if you go to non-Hermitian system, the eigenenergy is no longer real, so you have both real part and imaginary part of the eigenenergy. So to get a band structure, you can plot either of them as a function of K. So for one band, you get two curves. Now, instead of plotting it this way, you can plot it in the complex energy plane. So you look at the complex energy, and then as the wave vector moves, the complex energy will trace out a curve inside the complex energy space. Now, in this case, you will get a closed curve because the wave vector here is periodic. A closed curve in a complex energy space has non-trivial topology. With respect to a reference energy inside the loop, there is a non-zero integer winding number tell you if the K vary across the first Boolean zone, how many times the complex energy goes around in this energy. This, in the recent literature, is called point gap topology. And it also has interesting edge physics by this bulk edge correspondence, and this goes by the name of non-Hermitian skin effect. So if you take an infinite periodic system and has a non-trivial point gap topology, now suppose you truncate the system. If you do that, let's say as a simple case, if you truncate it only on one edge, so you create a semi-infinite system, as it turned out, every state in the system become localized, and the eigenenergy of the localized state sits inside the loop. And the degeneracy at each complex eigenenergy inside the loop for the localized state is equal to the winding number. So in recent literature, this is referred to as a non-Hermitian skin effect, and that has been probed experimentally. Motivated by these experiments, what we set out to do here is to provide a complementary experiment to directly probe the point gap topology. And we do that by trying to implement this what's called the Hartano-Nelson model. This is a one-dimensional tie-binding model, but with a direction-dependent hopping strength that is different in magnitude going to the left or to the right. And doing so necessarily break both reciprocity and energy conservation. So for this system, if you plot out its complex value dispersion, this is the formula, and then if you plot it in the complex energy space, generically it's an ellipse or a circle. And to implement this system, what we do is we take a ring modulator, take a ring structure, and then put in both a phase modulation and an amplitude modulation. The phase modulation gives us the Hermitian part, the Hamiltonian, and the amplitude modulation gives us the anti-Hermitian part. And when you combine them together, you create a Hamiltonian so that these two coefficients become different. And with this, you can then again repeat the band structure measurement. So in this case, after you have obtained this kind of diagram, for each of the wave vector, you can then draw a vertical line, and you will see a peak in the frequency space, and the position and the width of this peak tell you the real or imaginary part of the eigenenergy. So, and these are some of the experimental results. This is the experimentally determined transmission as a function of frequency and time. And by extracting out experimentally the real and imaginary part of the eigenenergy, you can indeed see this kind of point gap topology in the system. So here we talk about some of the interest associated with the topology of a single band. The next question is to understand what is the topology when you have multiple non-Hermitian bands. Now, in a Hermitian system, this is a typical two-energy band structure. You have two curves, and you may actually have a gap between the curve. In a non-Hermitian system, as I mentioned, each energy becomes complex. So, of course, you can plot out the real part and the imaginary part of energy as a function of k. Then you basically get 4 curves instead of 2. But instead of doing so, you can generate a more interesting plot. And this is by looking at complex energy plane, and also with a vertical axis being the wave vector. So you can think of this band structure then as a strand in this 3-dimensional space where the complex energy as the k move from 0 to 2 pi goes around in this 3-dimensional space. So if you have multiple bands, then you have multiple of these curves that winds around each other. So what you create, therefore, is what's mathematically called a braid. Moreover, because the complex energy, the set of complex energy at 0 and the 2 pi at the two ends of the first Boolean zone has to be the same, you can identify the endpoints of this braid to form a knot. So in general, when you think about non-Hermitian energy band, with multiple bands, then the natural mathematical language to talk about is the braid. This thinking about these bands in terms of braid, by the way, has a very strong connection to the topology of exceptional point that was in fact explored, for example, by Dr. Kunz here in some of her pioneering work. So as an example, these are all the braids that you can have in a two-band system. The two band may not wind around each other at all, so you get two separate loops, and you form what's called an unlink. They may wind around each other once to form what's called a unknot, twice to form a half link, and 3 times to form a trefoil. And in more than 2 bands, we have a theoretical paper to show that the topology of a multiple separable non-Hermitian band in 1 dimension, in fact, are classified by what's called a braid group. The braid group is, in fact, an extremely complicated group. Starting from 3 energy band, the braid group is non-abelian. So therefore, the band structure topology for non-Hermitian system is far richer compared with the topology of Hermitian system. In Hermitian system, for example, you would not see, without symmetry protection, you would not see non-trivial topology in 1 dimension. And here, and also most of the topological classification involve integer group. And here you will have a group structure that's far more complex. So motivated by some of these theoretical works that we have done, we set out to experimentally observe some of these braiding structure in non-Hermitian band system. For this purpose, as the simplest thing to do is to realize a 2-band braid. So we construct a Hamiltonian. We try to construct a Hamiltonian that looks like this. In this Hamiltonian, it's a 2-band system, so we have 2 sublattices. In sublattice A, we have this Hartano-Nelson kind of coupling, which is non-reciprocal. The sublattice B doesn't have any coupling within itself, but each lattice side coupled to exactly 1 lattice side in sublattice A. So by controlling the range of non-reciprocal coupling in sublattice A, we can achieve essentially every single 2-band braid in the system. And experimentally, since we have 2 sublattices, what we do is we put 2 fiber loops together. Each of them correspond to 1 sublattice. For sublattice A, to get the Hartano-Nelson kind of coupling, we put in both phase and amplitude modulation. For sublattice B, we don't need any modulation, so it's just a passive resonator, but we make sure that the length of it is stabilized enough so that its resonances match with that of sublattice A. So again, you repeat the band structure measurement, and this is some of the experimental determined band structure. You extract out the real and imaginary part of the case, now of the eigenenergy, and in this case, you will see 2 bands wind around each other exactly once, and that gives you a single loop. One of the very important aspects of the synthetic dimension idea is that you have tremendous amount of tunability. So to get, for example, a different Hamiltonian, quite often, instead of building a new structure, as I talked about initially when we think about photonic crystal, what you do is simply change how you modulate the modulator, how you control the modulator. Quite often that involves essentially changing a single line of code in MATLAB that controls the voltage that you use to drive the modulator. So for example, in this case, just by changing how we modulate, you can easily achieve other kind of braiding. For example, this is the half link where the 2 bands winds around each other twice, or a trefoil where they wind around each other 3 times, and so on. So I think they probably conclude the first major part of what I like to talk about, where we use this platform as a way to think about and explore non-trivial topological physics in physical systems in general. In the remaining part of my talk, I'd like to switch gear and talk about maybe slightly more applied aspect of trying to use this platform in the context of optical computation. So these days, there's a lot of interest in artificial neural network. For example, as a textbook example, you would send in an image, such as a handwritten digit, run it through a neural network, and it will spit out what each of the image correspond to. If you look into the algorithm that's involved is a cascade of a linear operation operating on the vector formed by the pixels of this image, followed by a nonlinear pointwise activation. And then you cascade this. So for this, the computational cost, especially the energy cost, is dominated by the matrix vector multiplication. And in optics, one of the interesting observations is that you are essentially doing matrix multiplication for free. You take any optical structure, you send the input light, and you look at the output light. You routinely relay the input to the output by the scattering matrix. Now, in doing so, what you are doing is essentially doing a matrix vector multiplication, and you can do that in free space. You can do that on the on-chip Mach-Zehnder interferometer array. You can do that for practically any structure. A piece of furniture, for example, can be characterized by this as well. So the nice thing about this is that this is entirely passive. Other than the energy that you put into the input signal, there's nothing there. And so in recent years, there have been a lot of interest in trying to use this type of structure for computing purposes. Here, one of the pioneering work for on-chip integrated photonics was done by Dirk England and Marin Soliacek from MIT. They use a Mach-Zehnder interferometer mesh to achieve matrix vector multiplication, and then together in combination with digital hardware, they were able to demonstrate a neural network. Some of our own effort in this area, 1 year after their initial demonstration, we proposed that you can train this kind of network in situ using backpropagation algorithms, so that you no longer need to build a computer model for this kind of network. And then 5 years after our theory work, we were able, in collaboration with Olaf Solger and David Miller, to provide an experimental demonstration of this backpropagation algorithm so that you could actually train this kind of neural network directly on chip without having to build a physical model on a computer of this network. So this is certainly a very promising and exciting direction to do optical neural computation. However, one of the difficulty about this kind of neural network is the difficulty for scaling up. Our own experiment, you can check out this paper, has a 6 input waveguides. So at most, it's implementing a 6x6 matrix. In reality, there is an auxiliary waveguide that needs to be used, so it's not even 6. Okay? Now, if you go back, maybe I should show that slide. If you go back to what people usually do in this hand digit recognition, they vectorize each of the image, and then they perform a matrix vector multiplication, and each of the image has 784 pixels. So if you naively saying, I'm going to try to implement this, then you would need 784 waveguides. And this is not something that you usually assign to your graduate student for your PhD thesis to make and control 784 waveguides. So with this as a background, we think that the idea of going into a synthetic space and going into frequency or time domain can be actually quite interesting. As an initial step towards it, what we have done is to theoretically explore the possibility of performing arbitrary frequency mode conversion. So we imagine that you send into a device a photon with an arbitrary frequency, and what we would like to do is to design the modulation in this device to generate the photon with another completely different spectrum. And to do so, in theory, losslessly, without losing that photon. And this is done by using this ring resonator setup and by controlling the waveform that you put in to this electro-optic modulator. And when you try to implement matrix vector multiplication, most of the time you would like to have a vector with well-controlled length. In a synthetic dimension, in a frequency cone, for example, you have some of the pioneering work here by Pascal. When you look at a frequency cone structure, you routinely have very large number of cone lines, which is great. But on the other hand, here you would like to have a very well-defined number of lines that only interact among themselves. So the first thing that one would need to do is to put in a boundary in the synthetic frequency space, and that can be at least in principle, easily done. What you can do is to put in a smaller ring coupled to a big ring, and the smaller ring will perturb some of the modes of the big ring, but only over substantial distance in frequency space, and that allow you to create a boundary between these two modes, so allow all the modes in here to couple to themselves. And this idea we have done both in theory, and last year also published a paper to show that experimentally you can get this done as well. Once you have done that, then you have a finite and well-defined number of input frequency mode, and similarly, similar number of output frequency mode, then you can define a scattering matrix of this system. In this case, we're talking about a unitary matrix because we try to not lose the photon. And for n frequency component, the number of degree of freedom in a unitary scattering matrix scales as n squared. And this number turned out to be quite important when you think about how to create such an arbitrary frequency conversion. So the degree of physical degree of freedom in the device are how you modulate each of the modulator, and that's the physical degree of freedom. And for each modulator, you can put in multiple modulation frequency or modulation tones, and for each modulation tone, you have the amplitude and phase. So consequently, the physical degree of freedom in the device, the number of them, are the number of modulator times the number of modulation tones times 2 to account for both the amplitude and the phase. What we do is to use a numerical algorithm, an inverse design algorithm, to choose all these parameters in order to achieve a given target matrix. So for example, this would be a 5x5 permutation matrix, and we play with all the modulation parameter until in frequency space, you can get a resulting matrix that look exactly like your target matrix. When you do that, the degree of freedom argument turned out to be very important. And it turned out in our numerical experiment, we define what's called a fidelity, which measures how close our design matrix match the target matrix. And what we consistently see is that we can get essentially perfect fidelity when the number of degrees of freedom, physical degree of freedom, exceed the degree of freedom in the scattering matrix. So for 5x5 matrix, for example, with you have a 25 degree of freedom in the scattering matrix, and we see that we typically can get very good fidelity if our physical number of degree of freedom exceed that number. But if it fall below, then you start to see much worse performance. So we show here that one, in fact, can perform arbitrary frequency conversion, or in other words, to program matrix vector multiplication with arbitrary matrix in frequency space. And we believe this is interesting in the classical computation side because it moves a large number of complexity from the spatial domain into the frequency domain. So much of the control of the system now become electronics that you just need to control the modulation waveform. And we also think this is potentially important in the quantum side because modulation fundamentally is a linear optical device that operates on single photon. So to end the talk, before that, let me just point out that as an initial step towards that, we have also recently considered a special group of operation, and that's convolution. So a convolution operation, for example, look like this. Suppose this is your input vector. You perhaps want to convolve with a kernel to form an output vector like that. And this is an important operation. What I'm showing here, in fact, is a convolution kernel corresponding to a Laplacian operation. So the output actually detects the edge of the input, and that's edge detection. So in a theory paper, we show that for any kernel that you care about, in fact, there's an analytic way of write down what the modulator, how you will modulate this modulator inside the ring analytically. And recently, we also provided an experimental demonstration of this kind of convolution in synthetic frequency dimension. And convolution is one of those operations that has been very important in neural network, for example, in convolution neural network for image processing application. So in maybe the last 10 minutes or so of my talk, I would switch gear, but also along the line of computation to talk about some of the idea of using synthetic dimension for quantum computation. So as a way of motivation, there's a lot of interest in thinking about using photons for quantum computation. Photons obviously is the optimum information carrier for communication purposes. So therefore, naturally, one would like to be able to do some computation with as well. Most of the existing photon-based quantum computing architecture have focused on this linear optics quantum computing protocol, where one build a very large interferometer and then detect and post-select the state. So this builds upon the tremendous advance in the past decade in integrated photonics and has generated substantial commercial interest, but it imposes huge resource overhead because it's fundamentally a probabilistic technique. So instead, certainly there has been interest to do a more quote-unquote traditional quantum computing architecture based on photon, and by trying to build deterministic photon-photon gate, for example. And this can be done by scattering photons against quantum emitter. And in recent years, there have been a lot of progress in constructing these kind of systems that can couple very efficiently a single photon with an emitter, scatter it, and create gate out of it. I'm quoting a picture here of a quantum dot integrated into a photonic crystal waveguide. But there are also outstanding work here from his group, for example, doing these kind of quantum optics experiment coupling to single organic molecules. By now, there has been very good work on single quantum emitter with desired characteristic. The difficulty is to scale up. So typically, you think of a single quantum emitter perhaps as a single gate, and the most naive way to think about building a larger scale circuit is then, well, you can go try to construct multiple of these gates. Now, the difficulty of it, this turned out to be quite difficult, and there are many levels of difficulty. One of them, in fact, is that it is actually difficult to create many identical quantum emitters to form a circuit. These quantum emitters, at the very least, tend not to have the same resonant frequency, so even get two quantum emitters to have the same resonant frequency take quite a bit of effort. So with this as in mind, and keeping in mind what I've been talking about throughout this talk, which is to try to move some of the experimental difficulty from out of physical space, what we propose to do is to try to build or at least try to imagine a quantum computing architecture using only a single quantum emitter, since, well, a single quantum emitter, at least experiment, there has a lot that has been done on it already. So in our case, the qubits are the photons stored in a fiber ring as pulses, and we control switches to switch the pulses and to scatter against an atom perhaps embedded in a cavity or quantum emitter embedded in a cavity. And what we show is that by manipulating a single quantum emitter, as well as all the classical control associated with the switch, one can create quantum circuits with arbitrary complexity. So in fact, it is possible to construct larger scale quantum computing architecture using only a single quantum emitter. So in our case, the qubits are time-indexed counterpropagating single photon pulses, and the computational basis is simply in a particular time bin whether the pulse propagate clockwise and counterclockwise. And in principle, the computing proceed by sometimes take the single photon pulse out of the ring with a classical switch, scatter this against the quantum emitter, and then put it back into the ring. And we show that this is sufficient to, in fact, perform arbitrary quantum computation on a substantial number of qubits. So in the scattering unit, there's simply a three-level system, perhaps inside a cavity with a single photon pulse scattered against it. And to create a single photon gate, we do what's called a gate teleportation protocol, where we scatter the photon against the atom, and in doing so create a control CZ gate, but it's essentially entanglement between the photon and the atom. We return the photon to the storage ring, and then you can apply rotation to the atom. And afterwards, you can measure the atom in a particular basis, and that actually teleport the rotation onto the photon. So in doing so, by manipulation of the atom only, you can actually create a single qubit rotation on the photon side. Two-photon gate can be done in a similar way. This is an adaptation of the well-known Duan-Kimball protocol, but in our setting. So you take one of the photons, scatter against the atom, rotate it. You scatter the second photon in, rotate the atom again, and then you scatter the first photon. At the end, you measure the atom, just like in the teleportation, to disentangle atoms and photons. So now we have both of these gate operations. We therefore have a universal computing architecture. And to implement any n-qubit unitary matrix or any quantum algorithm, it is known how you can decompose it or how you compile it into a cascade of single qubit gate and control CZ gate. And then we then further compile these single qubit gate and 2 qubit gate into physical operation onto our system. And the physical operation actually involve only open and close the switch, rotate the atom, or measure the atom. So here is a sample compilation of the quantum Fourier transform algorithm. So the important point to make here is that it is in fact possible to construct larger scale quantum circuits using only a single quantum emitter. So you can perform imperfection analysis. I won't go through the detail, but simply by saying what we actually did is to take the state-of-the-art number in different physical systems, and assuming you can put them together in the same system, then in fact you can get fairly substantial number of operation in these circuits. And moreover, this number perhaps can be further improved by error correction algorithm. So with that, I'm almost out of time, so let me briefly summarize. I hope to give you a flavor of something that we've been playing with in the past 6 or 7 years on this concept synthetic dimension. The essential point here is to be able to translate some of the difficulty, to move some of the difficulty from creating complex photonic structure into frequency or time space, where the complexity is now dealt with by controlling the switches in the time-dependent devices, and those control can be done electronically. We provide experimental demonstration that this kind of idea can be very useful in exploring interesting topological physics concept, and we think this is quite interesting for computation as well. So to end the talk, let me just put these slides up to acknowledge the number of people in my group that have contributed to this. In particular, I like to highlight Professor Lu Qiyuan, who is now a professor in Shanghai Jiao Tong University, who initiated our theoretical work in this area, and also Professor Vic Duct and Professor Kai Wang, now at Maryland and at McGill University, respectively, that really built up our experimental platform. And thank you for your attention.
Okay, thank you very much for the inspiring talk. I'm sure there are questions.
Thank you for the magnificent talk. Can we go back to the part when you've been talking about synthetic dimensions and like ring resonators? So you've been making this analogy with mode-locked lasers.
Right.
And I have a question regarding that. So in mode-locked lasers, you initially have a number of modes, like a ring resonator, but not ring resonator. And you have energy in each of these modes, and all you have to do is lock them together.
Right.
So how did you do this in your experiments? Did you use a wideband source, or did you just rely on creating sidebands?
When I say the connection to mode-locked laser, I don't mean we're doing mode-locked laser. I'm simply saying that part of the mathematics that we do for our system, people have used to describe mode-locked laser. So in our case, for example, we tend to do just a CW injection of light, and we measure the transmission of this device in both time and frequency. So in that sense, it's very different from a mode-locked laser.
So you excite the adjacent modes simply by modulation?
That is correct, yes. We excite the adjacent mode simply by modulation, and then we take a spectrum or we take time-dependent signal of the system.
And if you please, may I have an additional question?
Okay.
So regarding this two-dimensional Brion zone,
yeah.
Which you can probe by shifting the phase.
Yeah.
So it's not entirely clear for me. Like I see that there is blue color corresponding to 0 phase
Yeah.
shift and red corresponding to pi shift.
Right.
How do you access like more than 2 pi?
Oh, you change the phi from 0 to pi, and then it scans through between the two lines. So experimentally, what we do is we basically do this time-dependent transmission measurement, but then we repeat the experiment for different phi.
No, I mean like how do you go further than 2 pi?
You don't need it because, as you can see, in fact, by moving from the blue to the red curve, in fact, you already covered the entire first Brent zone.
Okay. Thank you very
Yeah,
much.
so that's enough. Yeah, so you could actually probe to the band structure this way.
Okay, very good, Gerd.
Yeah, thank you very much. I'm wondering about practical implementation of this unitary transformation of a single photon. In this case, it's important that this is very lossless. So if you think about time reversal, of course, if an atom emits a photon, you have a decaying and exponential, and in order to do the reverse, you have to go to growing exponential. But then it is very important to do this very, very losslessly.
Right.
How close can you go? How much has been done experimentally to show how far you can go?
So the closest set of work that I've seen are those that have been done on lithium niobate modulators. They show a 2x2 version of this. In other words, this is Marco Loncar's group at Harvard. They show that you could actually take a two frequency and mix them in a way that's analogous to a 2x2 Mach-Zehnder. So they have done that. And so our version of this, in a way, is a more elaborate version of that particular experiment. I don't know the detailed number of their loss. Lithium niobate, of course, is a very low loss modulation mechanism, but I suspect in reality, most of these losses are not modulation loss, but coupling in and out and those things. And that, of course, is a long-standing challenge in quantum integrated photonics that people work hard on.
Thank you very much, maybe Clara.
Thank you for the very inspiring talk. I was also wondering about the synthetic dimension aspect you talked about. The measurements you showed were under periodic boundary conditions in the dimension, I believe. Is there also a way to engineer edges?
Yes, so we have done that. I just didn't go into great detail to show it, but there are a few things you can do about it. The experiment that we did is simply put an extra ring in there so that you create boundaries here and there, and in between you have a finite structure. So we have done experiment to show a number of effects associated with that boundary. And that's something that you can see in this reference. There are other ways of doing this as well that could be quite interesting, but it's doable.
So you could, in principle, also observe like the non-emission skin effect and these things.
In principle, yes. We have not done it, but I think it's doable.
Thank you.
Yeah. We didn't do it because it was done already, so it's yeah. There's a slightly less motivation for doing it.
Yeah.
Yeah.
Thank you very much for this nice talk. So my question goes also in this direction. Could you comment a bit on the quality factor needed for the ring resonators and how this then influences the computation time, basically from you feed the information in until you get an output?
Right. So in the end, if we really want to do this, it will be controlled by the quality factor of the ring. In a fiber setup, of course, the quality factor is quite high because even a single round trip takes a lot of time. So that controls your speed. But it would be interesting to think about an on-chip version of these kind of things.
Thank you.
Right. Thanks a lot for a nice talk. I would like to ask more about this quantum computation that you had at the end.
Okay.
So this experiment or this proposal for an experiment resembles quite a lot what one would do with like measurement-based quantum computing, with first generating a cluster state and then doing computation by measurement. So could you elaborate a bit more? What is the difference here and what the key advantages?
Here, the intention was not to do this measurement-based computing where you first generate a cluster state and the algorithm is the measurement. Here is really, at least what we envisioned, was truly a gate-based protocol where you basically operates on a m-photon Hilbert space and then get the desired state at the end. Of course, these are connected. It is quite conceivable to use this as a generation for cluster state, in which case you could then do your measurement-based algorithm, because in essence, what we're doing here by looking at individual gate is to create entanglement between different photons. So you could actually envision this in that context as well.
Are there some clear advantages of one of those approaches?
I will need to think about it. I'm not sure either one. Obviously, I think this is a challenging proposal. So being able to demonstrate this, even let's say to entangle multiple photons in this way, could already be quite interesting.
Thanks.
Thank you for a nice talk. I have a question about this series of resonators to implement a multiplication by the matrix. I think each individual resonator should only have coupling coefficient depending on the difference between the modes, but not on their absolute shift. How do you then generate an arbitrary matrix with a series of this?
What we generate is let me think about how, it is an arbitrary n by n unitary matrix. So that you can generate because you, by putting boundaries in, you restrict already let's say 5 by 5. You put a boundary so that only 5 modes talk to each other. And within that 5 mode, then you can allow them to mix arbitrarily. So there's no translation degree of freedom to go elsewhere. I'm not sure they answer your question, but that's how the setup works.
Yeah, I think so. So this is because the boundary conditions.
Yeah, it breaks translational symmetry. In the experiment that we did on the convolution, it does not. So it's a simpler experiment.
Okay. I see that in principle we have a few questions from the internet. Maybe you can take the first one and read it.
Yes, my question is, do reach in general relativity speed in your experiments?
Can you maybe repeat the question?
Do electrons reach in general relativity speed in your experiments?
I don't think we can hear the audio, so maybe you just want to read.
Yeah, I have the question. Do electrons reach in general relativity speed in your experiments?
Electrons, no. No. I guess I'm not 100% sure what this refers to, but because the electron enters through modulation, so we do drive the electron in and out. I don't think those are relativistic speed electrons.
Maybe you want to read the, I think there are more questions.
Can the quantum ray computer also perform continuous variable quantum computing using squeezed light?
So when we construct this, this is not intended for continuous variable kind of quantum computing architecture. It wasn't intended that way. But in fact, on the frequency synthetic dimension side, it is actually quite related to some of the continuous variable architecture. For example, if you build in squeezings and things like that. So that is an interesting direction to explore.
Okay, so maybe that's enough for the online questions for the moment. If there are more questions from the room. Otherwise, in view of the time, maybe I'd say we close the session here. There is food outside.